that is y is equal to e to the x. Okay, now why is this a special function? It is special because of mainly this e here. Okay, what is this? This is Euler's number or Euler's number. Okay, sorry, Euler's number. Okay, that's his name, and it is an irrational number, just like pi. So like pi, irrational. Okay, which means it has infinite digits and we cannot find a pattern in those digits. Okay, so it's irrational. Okay, and it's so special because it pops up whenever you least expect it. Okay, so it pops up in finance, in compound interest, in growth and decay, anything where things are being multiplied constantly, it pops up. Okay, that's why it's so fascinating and it's such a special number. But for our cases, it's a special number because its derivative has a significant property that almost no other function has. Okay, and we're going to investigate that today, and we're going to find out what that property is and why it's so significant. Okay, so here, this is the graph of y equals e to the x. Okay, now as you can see, it's an exponential graph, increasing at an increasing rate, all of that. Very simple. What we are going to do is, like we do with all functions, and when we talk about differential calculus, we are going to draw tangents. Okay, we are going to draw a tangent. Let's start at x equals 0. Okay, so we have drawn this tangent at x equals 0. All right, now what can we find out from the tangent? Its slope, which is the derivative of y equals e to the x at 0. Okay, we already know that, we've already covered that. So let's try and find the slope, which will give us some insight, okay, into the derivative of e to the x. Okay, so we have a slope m is equal to, let's use this point first. Okay, same old, rise over run. Okay, nothing too complicated going on here. That doesn't seem right. I've made a mistake. And you get -1 and 0. Okay, which gives you 1 over 1, which is 1. Okay, so we are saying that the slope of this tangent is 1. Okay, which means the dy on dx at x equals 1 is equal to 1. Okay, it's important to note here that y, so e to the x, so let me just write e to the x instead. Okay, e to the x at x equals 1 is also equal to 1. Okay, now I'm sure some of you might already be having guesses. Okay, so we're just going to keep going and we're going to see if this pattern holds. Okay, so let's draw another tangent. Let's this time draw it at 1, okay, at a different place, and we're going to do the same thing. Okay, so we've drawn this tangent, and I just would like to mention before we start finding the slope all over again that this is e. Okay, it's just been rounded down to 3 digits. Okay, it, like pi, has a very long list of digits, decimals, but it has been shorted down to 3 decimals, and just so we could put it on the graph. Okay, so nothing to be concerned about. So let's just find the slope again. So m is equal to, this time it will be e and 1, okay, and 0, 0, which gives us e. Okay, so the slope of the tangent at x equals 1 is e. So the same thing as before, the derivative of e to the x at x is equal to 1. Oh, did I write 1 there? Oh shit, this is supposed to be 0. Good, that's where we found it. That's my apologies, okay? So at x equals 1, the derivative equals e. Sorry, not x. Okay, the derivative equals e. E to the x itself at x is equal to 1 equals e. Okay, because you put that 1 there at the x, and anything to the power of 1 is just itself. So the pattern we were assuming still holds. Okay, and now we can see it more clearly that the derivative at any point, okay, at any x is the same as the function value at that point. Okay, now let's try one more. Okay, let's try one more tangent, and if this works, then we will say that it is a rule. Okay, although we have talked about this, for a rule you need to prove all values, but let's just have a look at this one. Okay, so let's try and find the slope again, and this time this is e to the 0.5. Okay, because the x value is 0.5, therefore the y value is e to the 0.5. That's the definition of the function. Okay, e to the 0.5 over 0.5, and we do our usual negative 0.5 over 0. Okay, that gives us e to 0.5 over 1. Okay, e to 0.5. So it looks like our pattern is holding. Okay, so we are saying that the derivative of e to the x at x is equal to 0.5 is equal to e to the 0.5. Okay, and e to the x at x is equal to 0.5 is also equal to e to the 0.5. So we have done 3 different tangents, okay, and all of them suggest the same thing, that the derivative of e to the x at any x value is the same as the function value itself. Okay, now let's just write that down. Okay, for now we are not going to prove it, okay, because the scope of this proof is beyond mathematical methods. Okay, it is much more, it's not as complicated, it's just not a part of this course. Some of the things you use here are not seen, so it's a bit unfair to show that proof, and not necessarily at all. It's just important to know here that if you have your function, okay, if you have your function y is equal to e to the x, okay, as we have seen, dy on dx is equal to the function itself, e to the x. This is the special property of e to the x, that when you derive it, it remains e to the x. And this is an appropriate time to show a traditional meme that whenever we discover this fact, we show this meme. Okay, a wild exponential function appeared, you use differentiate, it's not very effective because the function doesn't change. Okay, I know it's not that funny of a meme, but it's a traditional one. Okay, my teacher showed me, she found it from other places. It's like, you have to show it. Okay, let it be. More importantly, this allows us, for our interest as a lazy mathematician, okay, for me, that means that whenever I have to derive something as e to the x, effort is minimal. I just write the same thing down again. Okay, now, okay, so this is very easy. Okay, this whole process, very, very easy. All right, but what if we try and mix things up, and instead of an x here, we do x cubed, or instead of an x here, we do e to the, I don't know, like x squared plus 3x. Okay, what if things start to get complicated like that? Well, no need to fear. We realize that there's a function and another function. Okay, function and function. There's functions within functions. So what do we use? The chain rule. Yep, exactly. So let's try that. All right. Let's use our acronym. R for replace. Okay. Let u equals x cubed, and then y we know is e to the u. Okay. and then we differentiate both of them independently. This is our I, the inner function. Okay, du on dx is equal to 3x squared. Okay, this is our outer function, hence the O. Okay, you get u e to the u. Okay, sorry, I should use proper notation. Dy on du is equal to u, sorry, what was the u? E to the u. Okay, because we just saw that when we differentiate it, stay the same. Okay, and now we, where did it go? Oh, there we go. Okay. And now we use our together step. Okay, and we start with what we're trying to find, dy on dx, and we get our outer function, put it together with our inner function, and we get e to the u times 3x squared. And again, we introduce the u, so we replace it with the x, with x cubed, like it is here. E to the x cubed times 3x squared. 3x squared. Now, I would like to again get rid of the crosses because it may confuse you with the x's, so we just write it like this. Okay, and just before we finish, I would like to write it in this form for no particular reason. It just feels better this way. Okay, so that is the derivative of one of them. Okay, simple. You use the chain rule. And I want you to try this one on your own. Okay, give it a shot. Same process as last time. Don't worry, it's very simple. Have a crack at it. Okay. All right. I hope you had a good shot at it. Okay. What we are going to do is the same thing as we did before. Okay. Let u is equal to x squared plus 3x. Therefore, y is equal to e to the u. Okay. Du on dx is equal to 2x plus 3. Dy on du is equal to e to the u. Okay, straightforward stuff. And dy on dx is equal to dy on du times du on dx, which is this this times 2x plus 3. Okay, and you are then left with, again substituting in the u, you then get 2x plus 3 times e to the x squared plus 3x. Okay, straightforward stuff. Okay, nothing that complicated and really simple. Just use the chain rule. Happy days. Okay, now as usual, we're going to notice something. Okay, we are going to notice that when we have y is equal to e to the x cubed, I believe it was, e to the x cubed, this, first of all, stays in the derivative. And we kind of expect that, because when we derive e to the x, we get e to the x. Okay, so that stays in the derivative. And the same thing happens here. Okay, when we have y equals e to the x squared plus 3x, this whole thing stays in the derivative. Okay, that doesn't change. What does change is we then add, you would have thought of it that we get this value, okay, whatever's being raised, okay, whatever e is being raised to, we derive it and then we put it here. Okay, same thing here. We have this, we find this derivative, put it here. Okay, now that is an important observation, and we can conjecture again that when we have y is equal to e to the f of x, any function up here, the derivative will include this, so that stays the same, and then we derive it and multiply that, so we get this. Okay, f dash of x e to the f of x. Okay, order doesn't matter, but just I don't know, it goes off the tongue better this way. All right. So we have our conjecture, and as usual, we're going to prove this, and then we're just going to do some practice, okay? So let's start with again, there's a function within a function, so the chain rule. Okay, and we have our r, which is replaced again. U is equal to f of x. Sorry, let u is equal to f of x, therefore y is equal to e to the u. Okay. Du on dx is equal to f dash of x. Derive it. Okay. Dy on du is equal to e to the u. Simple stuff. And now dy on dx is equal to dy on du times du on dx. That's a horrible x. Okay, dx, which then gives us our result that we're looking for. Dy on du is e to the u times f dash of x. And then again, we introduce the u, so we're going to get rid of it by substituting this back in, e to the f of x. Okay, so simple, we have proved our conjecture, and we know that this holds true for any f of x. And now, instead of doing the whole chain rule, we can just use this simple rule for differentiating e to the f of x. Again, just keep this as it is, derive this, and multiply. Okay, simple steps. Now, this is exactly why I find e to the x so fascinating, and I just love this function. Why? It makes life so easy. Okay, like you don't have to do anything. It's just straightforward steps. Okay. Now, if you still don't like it, okay, you still don't understand its value, you're like, okay, I mean, it just stays the same, or it's just an easier step. Okay, what's the whole fuss about? Do some practice questions, okay, and you'll see how much easier it is. Okay, see how much quicker it is. It's like butter, you know. It's just easy steps. Okay, now go again, but seriously, do the practice questions. Okay, get comfortable with this, and if you get comfortable with this once, memorize this rule you have here. Okay, memorize this rule you have here. You will not have to look at this ever again. Okay. That is my promise. It's a very simple topic. Just go hammer it out. Thank you.